Today we shall start our discussion on interpolation. Let me first explain what is meant by interpolation. Sometimes it is found that a pair of XY data are available for as for example, consider the census performed in India. Say for example, we have data available in these data are the populations are available. So we call this as xi. This is x0 is 1900. These are the years, and the census are performed at an interval of 10 years, and that we have corresponding population in crores. As for example, 26 crores, the population in crores. Say such data are available. Sometimes people ask a question that what would be the population or what might be the population in a year 1915 or something like that. That is the question. The question is to read between the lines. We have a tabulated data and one asks a question about the value of y, if we call it x independent variable, and this is the population yi. What is the value of y at a value of x which is not tabulated here? So to say, interpolation may be looked upon as a technique of reading between the lines. So we formulate the situation as this. We have a given set of data xi and the corresponding yi, and the data is available for I is equal to 0, 1 up to n. So there are n plus 1 pairs of data, xy data. Our aim is to find out the value of y at a value of x for which x is not any one of the supplied one. That is, we are not interested about the value of y at 1910 because the exact data is already available. This is the technique. There are two different approaches to address the problem. One is the process of curve fitting. In the curve fitting or least square feet, as you have done already in earlier classes, one plots x value and the corresponding y value, then one gets a scattered curve like this, and one tries to plot a graph which passes through the scattered data so that the sum square error is a minimum 1. So one gets a formula for y in terms of x. So one gets y as a function of x, so that the sum square error, sum square error is, this is the actual value of y, yi minus f of xi modulus square is a minimum. This is the principle of curve fitting, and we have heard about the least square fitting technique, in which the parameters of function f are adjusted so that the sum square error is a minimum possible one for the given set of data. In interpolation, another technique is used. In interpolation, one assumes a form of y, the function y, this forms of y, and the unknown coefficients of this function are so adjusted that if we use the value of x5, then we exactly get the y5. That means in interpolation we flip the curve such that the supplied data are reproduced exactly, and in between the points the curve is approximated. So there is a difference between interpolation and the curve fitting. In curve fitting technique, one assumes a curve which may not pass through the actual experimental data. But in interpolation, the curve is so chosen that it exactly matches to the values of y for the given for each and every given value of x. And in between the two given values of x, the function is approximated by a function called interpolation function. This is the basic technical difference between curve fitting and interpolation. We may also call that curve fitting is a holistic approach to look at the problem, so that where in curve fitting one considers all the points and make the error, sum square error, a minimum one, so it is an holistic approach. Here, on the other hand, the interpolation may be looked upon as a local approach, in which each and every supplied data is reproduced first, and in between the supplied data the curve is approximated. So this is the basic difference between interpolation and curve fitting. Now we come to the basic principle. We have learned in the Fourier series that any function in the basic interval 0 to 2 pi can be represented as a linear combination of sine functions and cosine functions, as sine function and cosine function forms a complete basis of orthonormal functions in the interval 0 to 2 pi. And that is, any function between the limits 0 to 2 pi can be expanded in terms of sine of nx or cos of nx. If the function is odd one, sine nx is sufficient one. If it is the even one, cos x nx is sufficient. If the function is neither sine nor cos, neither even nor odd, then both are required for the expansion. As a function, any function can be written as a combination of even function and an odd function. In interpolation also such a function exists. That is, we say that if we have a data, x data and y data, and if we rescale x values between 0 to pi, then the corresponding y value can be written as a linear combination of sine function and cosine function. This is the corresponding function is called a trigonometric interpolation function. The interpolation function is the function, the approximate function that we use to represent y values. So the interpolating function in such cases is a trigonometric function, just similar to that we have used in the case of Fourier series. The function, the interpolating function may also be a polynomial, and we call it as an interpolating polynomial. Now we come to the case that we have if we have a analytic function in the range a to b, then we can expand this analytic function in Taylor series. That is, we can expand f of x as a0 plus a1x plus a2x square and so on and so forth. It is the Taylor series expansion, and if we know the function beforehand, we know the expansion coefficients. Even if we do not know the function, we can, if we have n values of n plus 1 values of f, if we have n plus 1 pairs of values of xi and corresponding yi, this enables determination of n plus 1 constants. So that if we have n plus 1 pair of data, we can at most calculate n x to the power n. So we can approximate the interpolating polynomial by a polynomial of degree n. The corresponding principle is called the Weierstrass principle. Weierstrass principle. This is an equivalent of Taylor series expansion. Taylor expansion in analytical mathematics is being replaced by Weierstrass principle. The principle says that if we have a given set of data, then we can approximate if we have a curve or a set of data, then this curve can be approximated or estimated by a polynomial, so that the error at each and every point can be made as small as we please. Let me explain the curve. Say this is the y versus x curve, and this is the actual nature of the curve, and we approximate the function by a polynomial which is called a phi n. This is the actual function y of x, the actual one obtained from experiment. Actual one which is obtained from experiment, and this is the range of interpolating polynomial. For Weierstrass principle, it is phi n because it is a polynomial of order n. The Weierstrass principle says that this is the error bar, the curve is within the error bar. The principle says that we can reduce the error to as small values as we please. To reduce the error, we need more and more data. As we have already stated that if we have 5 pairs of data, then we can calculate at most 5 constants, so that the in polynomial that we can assume at most will be of degree 4. Depending on the pairs, depending on the number of available data, we can have a better and better polynomial. The larger number of data available, that is larger than values of n, the larger will be the order of the polynomial, and there will be better, that will be estimated better and better. Now we are interested only in polynomial interpolation, that is, the exact function y will be approximated by a polynomial function phi n, which is a polynomial as per Weierstrass principle. And if we are supplied with n plus 1 pairs of data, then we can at most assume phi n to be a polynomial of order n. We cannot increase the degree of the polynomial. The restriction has been put forward by the number of available data. If the data, the supplied data are not sufficient one, we can get totally wrong result. As for example, consider the situation consider the COVID situation in India around now October, November. Around October, November, when the number of cases in India were increasing monotonically day by day. If we were supplied with the data up to that much, then the interpolating polynomial would have a tendency of an would have an increasing tendency, as is evident from the data available in next. But this curve does not show any lowering trend because the number of data is not sufficient enough. We were provided with data in this range only, so which says that the polynomial has a increasing trend. But if we include the data till date, then the curve would also show a lowering trend. So depending on the number of available data, we may have a better and better polynomial. We are considering another example. Say we have a data like this, experimental data, and we are provided with only two pair of data. So we can at most fit a straight line, because if as we have given only two data, we can approximate phi as a polynomial of order 1, and this is a0 plus a1x, which is a straight line. The data is not at all fitted satisfactorily. If we were provided with three pairs of data, then the polynomial could have been a parabolic one, and we expect that the matching is a better one. And if we go on increasing the number of data, the actual data points will be matched better and better. It may so happen that the actual graph is a straight line. We have a straight line graph like this, and we are provided with 10 pairs of data. So the actual form is y is equal to mx plus c, and we are provided with n pairs of data. That is, say for example, we are provided with 6 pair of data. Then we approximate phi n by a polynomial of degree 5, and we write it as a0 a1x plus a2x square a3x cube a4x to the power 4 a5x to the power 5. And upon calculation, it will found that a2, a3, a4 and a5 will have very negligible, very small values compared to a0 and a1. By this we conclude that the function itself is a linear one, while the excess number of data has proved that the higher coefficient are really very small. We shall come to an example afterwards. We shall consider an example of this sort afterwards. So this much is the a brief introduction about interpolation. Let me summarize once again. In statistics or numerical techniques, generally we have a n plus 1 pairs of data of xi and yi are available. In interpolation, our aim is to have a value of y between two tabulated values, and In curve fitting case, we assume a form of the function and say that the sum square error should be minimum 1, wherefrom we try to estimate the shape of the curve. This is a holistic approach because we are summing the square of the error, so this is a holistic approach. Another one, the interpolation technique, we approximate the function by approximate the actual function by a suitable function. It could be a trigonometric function, then we call about trigonometric interpolation. If it is a polynomial, we call it a polynomial interpolation, and there are other forms of polynomial. One may expand a function in terms of Legendre function, then we speak about Legendre polynomial. If we use Bessel functions to expand the interpolating function, then it will be better Bessel interpolation, and so on and so forth. The basic condition that should be satisfied in interpolation is that at each and every value of xi, the supplied one, the interpolating function should exactly reproduce the value of yi, and in between the form is determined by the share. In between two values, the function values is estimated as per the choice of the interpolation. In regard to in a polynomial interpolation, there is a principle called Weierstrass principle, which is the analogous of Taylor series in analytical mathematics. The Weierstrass principle says that any given function can be estimated by a polynomial of suitable degree. So that the error between the actual function and the interpolating polynomial can be made as small as we please. To reduce the error, the expansion coefficient should be the proper one, and the order of the polynomial is being restricted by the number of data supplied. We shall discuss two polynomial interpolation formula as prescribed in the syllabus. One is the Newton's forward formula, and other one is the Lagrange's interpolation formula. Say we are provided with n+1 set of data, and the data supplied may be an equispaced one. As for example, the Indian census, the example that we cited in the Indian census, in which case the census is performed at an interval of 10 years. In which case the x values are equispaced. That is, if we start with x0, then we add some quantity to get x1, and then we add the same quantity to get x2. That is to say, the x values are in arithmetic progression. In such cases, we call the arguments are equispaced arguments, and for equispaced argument we use Newton's forward formula. In other case, the arguments may or may not be equispaced. That is to say, the difference between two consecutive x values may not be constant, in which case we call inequispaced arguments, and for inequispaced or unequal in x values we will discuss Lagrange's interpolation technique. So with this introduction we come to equispaced interval. And so equispaced arguments. Newton's forward formula. Before going to Newton's forward formula, we need to have a brief homework. First thing, what do we mean by equispaced intervals? Our basic assumption is always in this discussion that we have an n plus 1 pair of data xi, yi. There is an n plus 1 pair of data. Sorry, n plus 1 pair of data. We call x0 is equal to a and xn is equal to b. So the data are supplied between a and b. We define h to be like this, b minus a by n. So this is the width, width. So that we define x1 is equal to x0 plus h, x2 we define at x0 plus 2h, and in xi is equal to x0 plus ih, and xn is equal to x0 plus nh. This is, recall that this is can be also written as this. Now these intervals are equispaced intervals. The corresponding values of y are x0 is equal to, the corresponding values of y0 is equal to function at x0, y1 is equal to function at x1, and in this way yi is equal to function value at xi, which is function at x at a plus ih, and so on and so forth. There is a increment technique we use in calculus. That is, if we have x is equal to a, then as we shift from a to h, where h is equal to delta x, it is the value of x, and we move to a neighboring value of x. So we call delta y. So delta y we mean the value of function y at value a plus h minus y at a. So this is the delta evaluated at x is equal to a. So this is the difference formula we use in calculus. There are similar difference formula available in numerical technique. Let me first introduce this one. We call delta of y0 for equispaced interval, we define as delta of y0 means y at a. y0 means y at x is equal to a, and we call it y at a plus h minus y at a. That is, this is y1 minus y0. If we use this one repeatedly, that is y2, this is delta operating on y of a plus h minus y of a. If we use delta on this, it is y a plus 2h minus y of a plus h. This is from the first term. For the second term, we have y of a plus h minus y of a. Because here the argument is already a plus h, if we operate delta, then we have a plus 2h and minus a plus h. So this is this is the value. This can be written as, this is y2 minus twice y1 plus y0. So this has a remarkable similarity with the binomial expansion. y2 minus twice y1 plus y0. This is the difference formula is carried over with respect to y0. Similarly, if we calculate the third order difference of y0, that is delta 3 of y0, first this will be operated on this and we get y3 minus y2 from this part, then minus 2, this is y2 minus y1 minus y1, and then plus y1 minus y0. So this becomes y3 minus 3y2, then plus 3y1 minus y0. Exactly the binomial theorem is being reproduced. So this is y3 minus 3y2 plus 3y1 minus y0. So we can continue the difference in this way, and we call y delta k of y0 is equal to delta k of y0 is equal to summation over L is equal to 0 to k minus 1 to the power L kcl y to the power k minus L, y of k minus L. Now let us check this. This for L is equal to 0, it is positive, and alternatively positive and negative sign appears. The sign changes alternatively. Then the constants. This is N3C1, this is 3C2, this is 3C1, this is 3C3. So this is the form of difference. This is called a forward difference, because if, as we are considering delta y0, we are using the values of y on the right of y0. That is why it is called forward difference operator. If we are provided, this forward difference formula is applicable only when we are provided with a equispaced data. The things can be calculated very easily using the forward difference table, which I have used in calculating the spacing between the zeros of Bessel function of different orders, and wherein we have first plotted the zeros of Bessel function of different orders, and in the second column we have estimated the values between two consecutive zeros, and we saw there that for J0 the difference between two consecutive zeros of Bessel function approaches pi from the right hand side, and for Bessel function of integral orders other than 0, the spacing between two consecutive zeros approaches pi from the left hand side. The difference table can also be calculated in a similar way. Let me first explain the difference table. A simple difference table is very much helpful in obtaining